Okay folks, we are going to look at our next section. We're on page 240 of your book, and we're looking at the handshake lemma. What does it say? It says, in any graph, the sum of the degrees of the vertices in the graph is always twice the number of edges. So, well, that's what we just saw. Eh? The sum of the degrees of the vertices in a graph is twice the number of edges. So we add the degrees together and we get to the number of edges. Okay, this is called the handshake lemma. Now, just to remind you what a lemma is a mathematical statement that is primarily of importance in that it is used to establish other results in mathematics. That's what a lemma is used for. Okay, so the handshake lemma is sometimes called the degree sum formula, and it can be written like that. So the sum of the degrees of the vertices, where V is an element of the vertex set, that sum we denote as E. Okay? Here we are using the notation dV for the degree of the vertex V. Okay, so if you understand that, then the next work that we're going to look at is okay. So let's see what this implies. One use for the lemma is to actually find the number of degrees in a graph. Number of edges, rather. To do this, you must be given the degree sequence of the graph. Now, the degree sequence is a sequence of the degrees like they're given it here. And they give it in descending order. Okay, so there's 1, 2, 3, 4, 5, 6, 7 vertices in this graph. Okay, so we say to do this, you must be given the degree sequence for the graph or be able to find it in some other bit of information. This is a list of every degree, generally not in an increasing order. So how many vertices and how many edges are there in this degree sequence? So there's 1, 2, 3, 4, 5, 6, 7 vertices. Okay, so how many edges are there? Well, we add this. This is 8 plus 9. 8 plus 9 is 17. 18, 19, 20. So the number of edges will be 20 divided by 2. So there's 10 edges with the 7 vertices. Okay, so that makes it 10 and 7 if you have the degree sequence of your vertices. Okay, let's look at the second problem. Now this is called the handshake lemma. He says, at a recent math seminar, 9 mathematicians greeted one another by shaking hands. Okay? Is it possible that each mathematician shook hands with exactly 7 people at this seminar of 9 mathematicians? So did every mathematician, there was 9 of them, did they shake 7 people's hands? That is the question that we need to answer. Well, let's discuss that. Each mathematician chooses one person to not shake hands with here. Okay, so they're asking us the question, is it possible that each one of these shook hands with 7 people? So there's 9 vertices in this case, and there's 7 edges, or 9 vertices, which each has a degree of 7 in this case. Okay, so the equivalent of this will be 9 vertices. Now every vertex represents a mathematician, and the degree of each vertex will be 7. So what does that mean? The total degree will be 9 times 7, which is 63. Now to find the number of edges from that, we'll have to halve that. Okay? and that gives us 31,5, which is just simply impossible. Okay, so he makes that argument here quite nicely. He says, if such a graph existed, the sum of the degrees of the vertices would have been n times 9 times 7, which is 63. This would be twice the number of the edges. So to find the number of edges, we will have to halve that. And that will give us 31.5 edges. So that's just simply impossible. Now folks, that's a very nice example of a real-world problem turned into a graph theory question and using graph theory to answer it. Okay, so let's see what we can generalize from the handshake lemma. Proposition 418. In any graph, the number of vertices with odd degree must be even. Okay, now he proves it by arguing the following. He says, suppose there was a graph with an odd number of degrees, of vertices with odd degree. Then the sum of the degrees in the graph would be odd, which is impossible by the handshake lemma. The sum of the degrees of the vertices has to be even, because every edge or every vertex is joined by two edges. Okay, very important. Okay, let's continue with this. We will consider further implication of the handshake lemma in some of the exercises. Okay, one final definition now, and I'm going to spend some time on these type of graphs. We say a graph is bipartite if the vertices can be divided into two sets, A and B, with no two vertices in A adjacent to one another, and no two vertices in B adjacent to one another. But the vertices in A can be adjacent to the vertices in B. But as long as in the set of A, if you've taken the vertices and you've split them, there's no adjacency here, and there's no adjacency here. The adjacency happens across the two sets. Now, okay, now we're going to go back to language we've used before. If each vertex in A is adjacent to all the vertices in B, then the graph is a complete bipartite graph and gets a special name. So if I talk about KMN, I'm talking about a complete graph, not just any graph, a complete bipartite graph. Okay, and the cardinality of set A is represented by M. Now remember, the cardinality measures the number of things in that set. Okay, so that's the number of elements in set A, and cardinality of B will be the second set, the number of elements in set B. So if we talk about K33, which was, we did that earlier with the houses and the utilities, then we have the houses in a separate set, okay, and the utilities will be in a second set. Now each one of these houses was connected to a utility node on the other side. So this house was connected there, and there, and this house was connected with that utility vertex, this vertex, and the third one. So what you can see happening here is that you are forming two separate sets here, and there's no adjacency in each one of those sets. Those two sets are separate completely. They are only mapped onto elements in the second set. And that is what a bipartite graph is, folks. So I'm going to spend some time now working with a few bipartite graphs and working with its definition, so you can see how it works. Okay, to look at our bipartite graphs, we're going to start by looking at a definition for bipartite graphs. Okay, so we spell it bipartite graphs. The bi refers to 2 and partite 2 parts. The graph can be divided into 2 distinct parts. Okay, and then the rest follows where the edges can, or the vertices cannot be adjacent. So a graph is an ordered pair. Let's just remind ourselves. G, which consists of vertex set and the edge set. The vertex set always first, the edge set always mentioned twice. Okay, so we say GVE is bipartite. Now what's the condition? If and only if, okay, biconditional here. There exists a partition of its vertex set such that, that's the symbol, the square one is there exists, such that each vertex in set V1. Okay, so we're breaking this up into 2 sets of vertices. So that each vertex in set 1, V1, joins a vertex in set V2. Okay, so each of the vertices that you've divided this vertex set into, vertex set 1, vertex set 2, so there's a mapping between 1 and 2. Okay, so what does it mean? The vertex set can be written as the union of set V1 and V2, where also the intersection of those 2 sets is the empty set. So there's no intersection that happens between set 1 and set 2. So one vertex can't belong to 2 of the sets. That's basically what this is saying. So if you add those 2 sets together again, you get the original vertex set. This means then there are no adjacencies as well. So this implies no adjacency in vertices in set V1 and also in V2. So those vertices aren't adjacent to one another. Okay, that's that implication. So if 2 vertices are adjacent, then the one vertex lies in vertex set 1 and the other one would lie in vertex set 2. So that gives you quite a nice and easy way to think about this. If you do have an edge that is made up of vertex 1 and vertex 2, then vertex 1 lies in set 1 and vertex 2 lies in set 2. They lie in opposite sets if there are adjacency. So if this partition exists in a graph, then the graph is bipartite. Now if we look at vertices, let's just look at a few examples. Let's say there's vertices A, B, I don't really need to name them, A, B, C, D, and there's vertices here. I'm drawing a silly graph, but yeah. And this is what's happening. Let's go there, let's go there, and let's go there, and here, and there. Now if you look at these, those 2 are adjacent vertices. So if I want to divide this into vertex set, I make sure A is here and E is here. E is then connected to C. Okay, but E is already in vertex set 2, so C must lie in vertex set 1. It's also connected to B, so B must be in vertex set 1 because E is already in vertex set 2. We can't have E in both sets. Then we have C here is adjacent to F, so F must lie there. D is by itself, but D is adjacent to E and to G. So that means D must lie in the first vertex set, which leaves G to lie in the second vertex set. Now let's count. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We could divide the vertices into two distinct sets, okay, that are consisting of adjacency vertices for each edge. So this is a bipartite graph. Definitely. Okay, if we look at another example, let's just draw on another example. I'm going to do one that I saw somewhere, either online or in a textbook, I can't remember. So let me do this one, and let's just do 1, 2, 3, that way. Okay, so this vertex is joined with that one, with this one, this with that one, there, and there. That's what we have at the moment. Okay, so let's call this again A, B, C, D, E, and F. Now we're trying to find, is it possible to divide the vertices into two sets? Well, let's start at the ones that are quite obvious. Okay, I'm going to put E in 1, it's adjacent to D, so D must be there. D is already there, and it's adjacent to C, which is over here. C is now here, which is adjacent to B, so B goes to the other side. B in turn is adjacent to A, so A is here. A is adjacent to F. So indeed, we could have divided the vertices in two distinct sets. So yes, it's definitely a bipartite graph. Okay, so I think that helps you think about the object that we're using and what it looks like when a graph is bipartite. So the definition for bipartite again is, it is bipartite if we can split the vertices into two distinct sets, V1 and V2. We can call it VA and VB if we want to, doesn't matter. Excuse me. Where each edge, where the edges belongs to the edge set of the original graph, and the vertices are then separated into, so you look at each edge and you separate the vertices into where they are adjacent into the two sets. Okay, I think that gives you a good idea what a bipartite graph is and what it looks like, and how do we find if it is bipartite or not. Okay, so what's left for us is to look at what do we talk about if we talk about a complete bipartite graph. Now remember, what is a complete graph? It's a graph where each vertex on the left joins with a vertex on the right. Bipartite. Okay? So our utilities and home example is a perfect example of a complete bipartite graph. So what does K23 look like? Now remember, the 2 and the this is the notion or the notation we use for a complete bipartite graph. Means set A has cardinality 2. So there's two vertices there. Vertex A and vertex B. The second set has 3 vertices. And each one of these runs as follows. They're non-adjacent. So vertex D, E, and F. You can see there's no adjacency here, and there's no adjacency on the other side. Okay? Now we want to know, if we just have this, how many edges are there in a complete bipartite graph? How many edges do we have? Well, let's have a look. Let's count them and let's see if we can find a different way of doing this. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6 edges. Okay, so let's see, how do we find this? So the number of edges is 6. Well, if we look at the cardinality here, the cardinality of vertex set 1, that cardinality is 2, and the cardinality of vertex set 2 is 3. So if I take 2 and I times it with 3, I'm taking the cardinality of the first vertex set, times it with the cardinality of the second vertex set. It seems to give me the number of edges that are in my complete graph. So, if I need to know the number of edges in a complete bipartite graph, I can take the cardinalities and multiply them. Well, let's see if that's true. If we have this complete graph, now we'll talk about whether it's bipartite now, and I join these, what am I doing? I'm joining them so that they are all adjacent. And in a bipartite graph, we do not have adjacency. Okay, so is this a complete bipartite graph? No, it's just a complete graph. The number of edges, we said, is we take the number of vertices, we multiply it with, it is a complete graph, so we're looking at K5. Okay, so there's 5 vertices, and each vertex has one less edge connected to it. The edges are doubled, so if I halve this, I get 10 edges in the complete graph. In a complete bipartite graph, it's easy, because you will have the cardinality of each set of vertices, so it just means you multiply those two with one another to get to the number of edges in a complete bipartite graph. Okay, so that covers our complete bipartite graphs. Let's talk about the next focus, and what I want to focus on next is just quickly talk about the complements of graphs like this. So K, 2, 3 is a graph with 2 vertices, 3 vertices here, and it usually does that. There's no adjacency between vertices in each set. Okay, so there's 3, there's 3. Okay, folks, so this is definitely complete bipartite, 6 edges. Okay, so I want to know, what does the complement of that look like? Now remember, just like in statistics, if you talk about the complement of something, it is something that is not in the set, is the complement of the set. So let's see what is not in the set. Well, if I think carefully here, the complement I'm going to draw on this side, but let's first start by looking at it here. First of all, the complement will contain all the adjacency lines. We agree? But there's one adjacency line that we did not work with, and that is the adjacency line that joins this vertex with that vertex. Okay, so we have the complement of this 2 by 3 graph looking like that, the red part. So, and we write it with a line at the top. Now let's go to the one that we've looked at before, the 3 by 3, the complete bipartite 3 by 3 graph. So we have 1, 2, 3, and we have 1, 2, and 3. Now the graph must be complete, so it means that the vertices must all join with the vertices in the other set. Okay, so we join that one, we join this one, and we join that one. Now the complement of this will contain those sides that are not in the complete bipartite graph as it lies over there. So first of all, this adjacency is not there. And then that side that joins 1 and 3, makes them adjacent, is also not there. Same here, there and there is not in this side, and that one is also not there. Now another way to represent this, we can represent it like this, but there's 3 vertices. So we can go 1, 2, 3 and just do that. So what did we do? We just pulled this one out and we created a little triangle of it. So there's the second vertex set, looks exactly the same. Okay, so this will be K3 and K3. Okay, the complement of the complete bipartite graph would look like this, where the lines that are not in here, connecting vertices, are in its complement. Okay, folks, that takes care of bipartite graphs. Now, if you look in your book, on page 241, after the proposition, he gives names to graphs. Okay? So let's just look at those names. Kn, what does it mean? It means it's a complete graph. So there's 2 important things. It's complete and it has n vertices. That's an example of that. Kmn is a complete graph, but it's bipartite and it has sets with m and n vertices. Okay, so K2, there's the first set 2, the second set is 3. It's complete because every vertex joins with every other vertex in the other set, and it's bipartite because we could have split them in 2. Okay? Cn is something that we haven't spoken about yet, but he says this is a cycle in n vertices, so it's just one big loop. There's 6 vertices, and each vertex then is joined with an adjacent vertex. It's a loop. There's nothing running across to make it complete. Okay, so they call that a cycle with n vertices, and it's just one big loop. Pn is the path on n plus 1 vertices, so there's n edges if there's n plus 1 vertices, always one less, just along a path. So that is called a path. Okay, it doesn't close here, so it's not a circuit or a cycle. They call it either a cycle or a circle. We'll talk about that later on. This is just a pathway that connects those 6 vertices with 5 edges. So P5 means 5 edges, hence there's 6 vertices. Okay, then he goes on the next 2 pages in your book, talks about, let me just zoom out here, the next 2 pages focuses on, why isn't this zooming? Focuses on graph theory definitions. Now some of them we've dealt with, some of them we're going to deal with in future. Make sure that you familiarize yourself with what these definitions are, and then start doing the exercises that's on page 243. By the way, please like the video and join my channel. Please subscribe to my channel and like my video.